Hello Bobcats. In this video we'll be discussing how to calculate the enthalpy of a reaction using standard enthalpy of formations. So to determine the delta H or enthalpy of a reaction, involves to determine the delta H of a reaction involves the use of standard meaning these values have already been determined, molar heats of formation. So we're forming a compound, so it's a formation of a compound, and we use delta H. This stands for standard temperature and pressure, and we'll go over that in just a second, and the F stands for formation of a substance. So what are we talking about when we use these standard molar heats of formation? Well, the standard heat of formation occurs when one mole of a substance is formed from its constituent elements in their standard states. Now, a standard state is the most stable state at which that compound exists at 25 degrees and 1 atmosphere. So the standard state is how the compound exists at 25 degrees Celsius and 1 atmosphere. Okay? And that's what that little zero means. It's that standard state. Okay. Now, an example would be if we know that we have water as H, hydrogen gas, plus oxygen gas, going to H2O gas, producing H2O gas. And if I look at this, or H2O liquid, I'm sorry, it should be liquid. H2O liquid. And normally to balance this you would write a 2 here and a 2 here. So we would have to remember we want 1 mole. I wrote it right up here, I underlined it, I'll even square it. 1 mole of the compound, of the substance. So in order to have 1 mole here, I had to cut everything in half. So that's where the half a mole comes from. Well, this reaction has the delta H of formation has already been determined. It's got a value of a negative 285.8 kilojoules per mole of that reaction. So when we are looking at other reactions that have liquid water involved in it, we can use this delta H to determine the delta H of the reaction, this delta H of formation. And there's a huge list of these. So and you will be given either a list or the list will be written on your problem. But if you'll see here, usually textbooks have an appendix called thermodynamic quantities, and those would be the delta H of formation, the Gibbs free energy of formation, and enthalpy of formation. We just care about the delta H. So the energy involved in formation of, let's say, calcium carbonate is a negative 1,207.1 kilojoules per mole, or I can say the energy involved in producing carbon tetrachloride gas down here would be a negative 106.7 kilojoules per mole. If I wanted to do it in liquid form, it would be negative 139.3 kilojoules per mole. If we look at the formation of water, let's see if we can find the formation of water. Where did we have water? Water should be on here. Well, real quick, the formation of carbon dioxide gas would be a negative 393.5. I thought water was on the first page. Maybe it's not. And that's the problem with some of these. If you got to find, here's water. So the water liquid is a negative 285.83. Water as a gas is a negative 241.82. So you got to make sure you have the right state of matter. And so you have the values, and then we just plug the values into an equation I'm going to show you in just a minute. But it's important to understand this idea that we're looking for the formation of a compound from its elements. A thing to understand too is that the standard heat of formation for elements is 0. For a pure element is 0. And it's because the reason it's 0 is because elements are already formed. You don't form an element, so you're not going to use energy to form an element. So they have a 0 value. But remember, we're looking at forming compounds. So, and the standard conditions, of course, are 25 degrees and 1 atmosphere. Now the deal is, we got to make sure, I guarantee you'll see something like this. We need to make sure that we have the correct problem or equation for the standard enthalpy of formation. So a lot of times you'll see examples like this. I want to go through it because it's so common. I want to make sure you understand this. Let's say, which of the following, I should do this in a different color, and I'm going to change my colors real quick so that we can do it. And I know I started, but I'm just going to put a red over this so you can see that I'm really going to switch over to red. Apologize for the color issue. It's formation. Which of the following, see, I even messed up here. Which of the following reactions represent a standard enthalpy of formation reaction? For represent a standard enthalpy of formation reaction for NO2 gas. So let's look at this. I'm going to write 4 reactions here, and we're going to decide which one's the correct one to represent the standard enthalpy of formation reaction. So let's say we have N nitrogen gas plus 2 moles of O gas to produce NO2 gas. Then we have this reaction to look at. NO gas plus 1/2 O2 gas produces NO2 gas. Okay? Or we have N2 gas plus 2 moles of O2 gas will produce 2 moles of NO2 gas, and the last one, 1/2 of a mole of N2 gas plus 1 mole of O2 gas goes to 1 mole of NO2 gas. Okay, so let me explain which ones are right, which ones are wrong, and why, and then pick the right one. So as I go through this, remember it's the formation of 1 mole of a substance from its constituent elements in their standard states. Well, nitrogen doesn't exist as just N as in its standard state. It's N2, and this would be O2. So this one is incorrect because the elements are not written correctly. Here we have nitrogen monoxide plus half oxygen goes to NO2. Remember, it's from its constituent elements. This is a compound, so this is incorrect based on the fact that it's got a compound in the formation. So remember, we're not using compounds to form it, we're using elements to form this compound. Here, N2, that's correct, O2 is correct, and it's balanced correctly, but remember, it's all per 1 mole of substance, and we have 2 moles of substance here, so that's incorrect. So the last one, 1/2 of a mole of nitrogen plus a mole of oxygen gives you 1 mole of NO2. This is the correct one because we have 1 mole of the compound and we have the correct states of and the correct elements that are forming this 1 mole of this compound. So you have to be able to identify the correct reactions that represent a standard enthalpy of formation reaction. Now, the next part of this is the equation that we use to determine the enthalpy for a reaction. So, to determine the delta H of a reaction, we use the following equation. So in this equation, we say that the delta H of a reaction is equal to the sum of the moles times the delta H of formation of the products minus the sum of the moles times the delta H of formation of the reactants. Now remember, these delta H of formation values come from that table. And so let's put it, this is the equation. And where most students make a mistake is right here. It's always products minus reactants, not the other way around. It's not reactants minus products. And these N values come from the coefficients in the reaction that tell you how many moles of that element or product compound is made or used. So let's do a practice problem. Let's use green. So practice problem. Determine enthalpy of reaction for the following, of the following. Okay, here's my reaction. We're going to take propane, that's C3H8 gas, plus 5 moles of O2 gas to produce 3 moles of CO2 gas, plus 4 moles of H2O liquid. Okay. And so my reaction, what we're going to do is the delta H of the reaction is equal to the sum of the products. So I'm going to put a bracket here, and we have our products are carbon dioxide and water. So I'm going to write 3 moles of carbon dioxide, and the value for the carbon dioxide that we determined from this chart was, where's CO2? Carbon dioxide is a negative 393.5 kilojoules for carbon dioxide. So that's going to be a negative 393.5 kilojoules per mole. Okay, the moles cancel. Plus, we're going to sum it, the other product, which is going to be 4 moles times, and water, we said just a minute ago, was a negative 285.8 kilojoules per mole. Okay, and then that's all my products, so there's my sum, and then I'm going to subtract, and then I'm going to do the reactants here. So I have 1 mole of the propane, and the value for propane, C3H8, if we have that, that's going to be right here. I know you probably can't see it on the video, but trust me, that's the value. It's a negative 193.85, and so we're going to round to negative 103.9, negative 103.9. So that has a value of a negative 103.9 kilojoules per mole, plus, remember, it's the sum of all the reactants here, and so that's 5 moles of oxygen, and remember, oxygen is an element, and so that's going to be 0 kilojoules per mole. And there's the sum of that. Now, let's go ahead, and so when I sum these two up, this times this, that's going to be a negative 1,185 kilojoules plus a negative, when I multiply these two, the 4 times this, a negative 1,143.2 kilojoules, and then these minus this, 1 times this plus 5 times 0, so that's going to be minus a negative 103.9 kilojoules of energy. And so in the end, this minus a negative becomes plus a positive, so it all ends up with a negative 2219.8 kilojoules of energy. And then, and because it's delta H of reaction, it's really, you can say kilojoules per, I know we cancel out the moles here, but remember it's understood as kilojoules per mole of the reaction, based on how it's written up here. So I don't know why I put a square around that. I meant to put a square around the answer. Okay, so that's how we do this. We're going to do one more practice, and you don't have to show all the units, because I just wanted to show you the units, how we cancel some of this, the information there. Let's do one more practice problem, and then we'll be done with this video. And in this case, I've already got it typed up, so I'm just going to pull the typed up one. And this is usually how it's presented on an exam or quiz, that you've got the information for your reactants and products available. And so we want to know what the delta H for this reaction is. So the delta H for this reaction, remember, is the sum of the moles times the delta H formation of the products, which products minus the sum of moles times the delta H of formation of the reactants. Okay, now so all we do is we take the values and we put them in. So the next thing is I've got, okay, here I've got 2, so I'm going to go 2 times the value of this, and that's going to be a negative negative 124.7 kilojoules plus 13. I did it wrong. Did you guys catch me? And this is the same mistake that students make, and I made the exact same mistake that students tend to make. So we got cross through this because this is a reactant. It's always products first. Products first. So we got to do the products first. So let's try this again. And I'm showing you how it's so easy to make that mistake, so you're aware of it and will not make that mistake again. Let's do the product. So now we're going to take 8 times carbon dioxide, which is a negative 393.5, and we don't need to put the units in this time because we know that they're kilojoules per mole and we cancel the moles. And then we have 10 times the value for the water, which is a negative 285.8 kilojoules per mole. Now that's the sum of the products minus, and I'm going to write products under here so we make sure we do this correctly, minus the sum of the reactants. And so that's going to be 2 times the value for the butane, negative 124.7 plus 13, well, the value for O2 is 0, and this is the reactants. And so our value, and I'm not going to do each one individually. I'm just going to show the work here. Show the products and reactants. So we've got 8 times 393.5. So this is going to be a negative 3148 plus 10 times that is a negative 2,858 minus 2 times that, so it's 2 times a negative 124.7, so it's a negative 249.4 plus 0, and so we get 3148 plus 2858. So you don't have to show all this work. I'm just showing it so you can follow along and see how we get it. So there is the negative 6006 kilojoules, and then minus a negative 249.4 kilojoules, and so minus a negative becomes plus a positive, and so we really have 6006 negative 6006 plus 249.4, enter, and so this is going to be a negative 5,756.6 kilojoules per mole of reaction. And that's my delta H of the reaction using the enthalpy of formation, standard enthalpy of formation. So if you see the word standard enthalpy of formation, this is the type of work you'll do. And we'll stop this video at this point. And again, this is standard enthalpy of formation problems.